Hello, for this worked example, we've got an 80 centimeter long, 1 kilogram metal bar falling at 2 meters per second, and it's going to strike the edge of the table as shown below. Assuming the coefficient of restitution is 0.9, what is the expected angular and regular velocity of the bar after impact? So for this, we're going to have a couple points that we need to define up front. So first of all, we're going to label this center point C. And this point over on the edge, A is where it's going to strike the table. The distance between these two is going to be 40 centimeters, or 0.4 meters. All right, so the other thing we need to define is our normal and tangential directions. So the normal direction is perpendicular to the surface, so going straight up, and then tangential direction is parallel with the surface. And then finally, we're going to define our initial conditions. So our initial velocities are all known for the bar. And so looking at point C, we're going to have the velocity of point C in the normal direction initial is going to be negative 2 meters per second. The initial velocity in the tangential direction, so VC Ti is 0, and the initial angular velocity, omega I, is also 0. So the easiest piece, we want to figure out basically these three components in the final state. So the final velocity in the normal direction, final velocity in the tangential direction, and the final angular velocity are the three pieces we're looking for. The easiest one is the tangential direction. So since the impact force will be in the normal direction, the tangential velocity will remain unchanged. So VTCF is equal to VTC initial, which is 0. All right, so in the normal direction, we're going to have to use two different pieces to basically solve for the angular velocity and the normal velocity. So the first one is going to be, we're going to use the coefficient of restitution here. So for that, I need to look at point A over here. So our coefficient of restitution is 0.9, and that is the negative VAN final over VAN initial. And so since this thing's not rotating or sliding, if the center is going down 2 meters per second, this is also negative 2 meters per second. Which means if I basically, the negatives will cancel out, I do 0.9 times 2, VAN final is 1.8 meters per second. So that means after the impact, this point is going to be going up at 1.8 meters per second after the impact. That's what the coefficient of restitution is telling us. I need to relate that to point C. And so this is going to be kind of general planar motion. And so VANF is going to be equal to VCNF, which is what I'm actually looking for. I want to know the final velocity of point C, not of point A, minus R omega final. And so R is my 0.4 meters. This is 1.8 meters per second. And so we can see that basically, and this is all going to be in the y direction, the velocity of point C minus R omega final is going to be the final, or is going to be equal to VANF. So I've got these two unknowns I'm looking for. I know the other pieces of this puzzle. So I've got two unknowns in one equation. I need to supplement that with a second equation, and that's going to be my conservation of angular momentum about the point of impact, so about point A. So Ka final is going to be equal to K A initial. And these are our angular momentum vectors. So expanding this out, it's going to be I omega final. And remember, these are vectors, so I do need to include that in there. Plus R C with respect to A. That vector crossed with the mass times V C final. And that's going to be equal to I omega initial plus R C with respect to A crossed with the mass times VC final, or sorry, VC initial. That's the initial side of things. All right, so remembering that these pieces are vectors, so let's go ahead and put some of these in there. So the easy one is this omega initial. So omega initial was 0, so this piece actually just disappears. I initially is going to be, it's a slender rod, so 1/12 my mass, which is 1 kilogram. So everything is in meters and kilograms and meters per second. So I'm just going to leave the units out for this. Times the length of 0.8 meters squared. And then omega final, I don't know. So omega final, I don't know, but I know it's going to be rotating. Everything in here is 2D. So my angular velocities are going to be clockwise or counterclockwise. It is the K direction, so K hat. So next I've got my cross product. So cross product of R, C with respect to A, and so that is going from point A out to point C. So that is going to, that vector is going to be 0.4, 0, 0. So 0.4 in the I direction. So 0.4 I crossed with the mass times VC final. So VC final was going -2 in the J direction. So our mass was 1, so it's going to be 1 times -2 J hat. All right, so this cross product right here, the result of that is going to be 0.4 times V, oh no, so I don't know, sorry, I've mixed this up. This is my unknown. It's not, the initial is -2. This one is just going to be equal to 1 times VC final in the J hat direction. So 0.4 VC final in the K hat direction is the result of this cross product. This piece up here, if I simplify, so 1/12 times 1 times 0.8 squared, it's going to be 0.64 over 12 omega final in the K hat direction. And so all of this is equal to, this piece is 0, like I said. So my R cross F piece, so R is again going to be 0.4 I crossed with 1 times initially it is -2 in the j hat direction. All right, and so this piece, I have no unknowns over on this side. So this is just going to be -0.8 k hat. All right, so all of these are in the same direction. They're all k hat. So this simplifies down to 0.64 over 12 plus, omega final. Can't forget our unknown. Plus 0.4 times VCF is equal to -0.8. All right, so this equation is the conservation of angular momentum about point A at the point of impact. So this equation, along with our coefficient of restitution equation that we had over here, so 1.8 is VCNF minus 0.4 times omega final. So this one should be also normal. Let me fix that real quick. VCNF. Those two equations, two unknowns, and I can basically do the algebra. I use an equation solver here. I'm going to find an omega final of -0.7125, 7.125 radians per second, and VCNF of -1.05 meters per second for this one. And then again, VCTF was 0. So these are my velocities. I've got my two normal and tangential directions of the velocities after the impact and the angular velocity. If we look at this kind of post-impact, so I have my table over here, immediately after the impact, what I'm going to have is that point C in the middle is still going down. So it's going down at 1.05 meters per second. And this is a negative angular velocity, so that means clockwise. It's going to be rotating at 7.125 radians per second clockwise. So just after the impact, 7.125 radians per second. And point C has no tangential velocity, so it's not moving left or right. And that is the velocity I expect after the impact of this collision. All right, that's all we got for this worked example. Thank you for watching, and I hope to see you again.